Everybody, today we shall discuss more of transistor logic, and we will cover TTL transfer characteristics and different operating parameters, TTL open collector configuration, how is it used, TTL tri-state and Schottky TTL. In the last class, we got introduced to TTL, and there we ended by saying that a phase splitter, this is the phase splitter that we see, is important when we talk about the TTL, when we talk about TTL activity, okay, and the totem pole output configuration. So, this is how we ended in the last class, and in this class we shall elaborate more on that. So, this is the phase splitter, and also we mentioned that this resistance cannot be made 0. So, this was there in the last class, we made a note of it. So, in this particular thing, if you look at the inverter characteristics, this is the inverter characteristics, there are 4 distinct zones. Okay. So, we shall discuss each one of them turn by turn. And the first thing what we start with is the case when the input voltage is 0. Okay. So, this Vi is 0. There is a reference to VB4, this particular voltage, this is VB4, that we shall discuss little later. So, this is your VB4. Okay. So, when Vi is 0, what is happening? Current is going in this direction, current is going in this direction, right, and this transistor, the base current is very small, the collector current is also accordingly small. So, this transistor will be having mode of IE. Okay. So, it will be firmly in saturation, right, and when it is in saturation, current is going in this direction. So, this transistor does not get enough current to be on. So, this T4 is off in cutoff, and when T4 is off, no current is flowing through this. So, T3 is also in cutoff. Okay. So, these are the two things that we can see. T1 is of course in saturation. What happens at that time to T2? T2 at that time is on, okay, and the current that is flowing past this T2 depends of course on the load, because T3 is off, whatever current is flowing past here depends on the load current. Okay. If for a typical load, the current over here is the base current, which is relatively small. So, IB and RC4, this drop is small. So, accordingly the output voltage will be drop across this diode and drop across this transistor base emitter junction. Okay. So, typically it is 5 minus 2 into 0.7, 3.6 volt. For a large amount of current, if it is drawn by the load, both of them can go into saturation. So, at that time these two drops will be 0.75 volt or so. In this particular discussion, this part of the discussion, we consider that the transistor, when it just begins to be on, the base emitter junction voltage is 0.65 volt. Okay. Just it starts operating, become active, 0.7 volt when it is active, and when it is in saturation it is 0.75 volt. So, this is how we look at the base emitter voltages for an approximate calculation of this transistor inverter characteristics. Okay. So, for that particular case, we have 5 minus 2 into 0.75, 3.5 volt will be available at the output when a load is connected and which is drawing a larger amount of current. So, accordingly, we find this point 3.5 volt at 0 volt over here in the transfer characteristic. Clear? Okay. Now, as the input voltage is increased, okay, so slowly current might get diverted in this direction. Okay. Now, when at this VB4 is 0.65 volt, just at this particular point, okay, so what will happen? This T4 will turn on, this base emitter junction will turn on based on this is what we have considered. Okay. So, at that time 0.65 volt, and this is the collector saturation drop, that is 0.1 volt. So, at 0.55 volt of Vi, what we see that T4 is just turns on. So, this is one breakpoint A over here that we see in the characteristics, clear. Okay. So, now we go to region 2. So, this is the region 2. So, in the region 2 what has happened? T4 has become active. Okay. So, current has started flowing through this. So, E4 and RE, this drop is there, okay, but this drop is not sufficient to turn this T3 on. It is still less than 0.65 volt. Okay. So, what will happen at that time? Only this one will be on and T3 is still in cutoff. That is what is region 2 over here. Okay. And at that time, of course, since this has started conducting, this drop is not negligible anymore. This IRC, this drop across this RC4 is not negligible anymore. Okay. So, at that time, if you look at the gain across this voltage gain across this T4. Okay. So, from our basic transistor amplifier principle, the gain is minus RC4 by RE. Okay. That is the gain that we shall see in a configuration like this, right. And the gain that we can calculate, this is 1.4 kilo ohm and this is 1 kilo ohm, right. So, as we keep incrementally increasing it, this particular transistor will offer a gain of minus 1.4, which you see the slope by which it is reducing. How long will it reduce? Okay, like this till this starts operating. When will it start operating? When this voltage is 0.65 volt, okay, plus minus. When this is 0.65 volt, how much current is flowing over here? So, 0.65 volt divided by 1 kilo ohm, right. So, that is the current, and that multiplied by 1.4 is the voltage that will be the drop across this at that time when it just starts operating, and at that time then output voltage will be 5 volt minus 0.75 minus this particular drop. So, 3.5 minus this drop. So, that is the 2.6 volt. So, when it just begins to become on, at that time this is the point that B is reached, that is your 2.6 volt, and at that time the input voltage is 0.7 volt over here and 0.65 volt over here, that is 1.35, that is VB4 that is required, and minus the saturation voltage over here 0.1 volt, that is 1.25 volt, that is what you will see at this breakpoint B. Is it clear? So, this is the two zones how it can be defined. Okay. Now we look at zone 3. Okay. So, in zone 3, T4 and T3 both are active. Okay. So, we are looking at this particular place. So, when both of them are active, so the resistance across this base emitter junction, okay, which is in H parameter term, which is defined as HIE, which we have defined here as RD, resistance as base emitter junction can be considered as a diode resistance in that equivalence. Okay. Otherwise, those who are familiar with H parameter representation, this is nothing but the HIE in the H parameter 2 port representation. So, this resistance will come in parallel with RE, okay, and because of which this gain will become RE parallel RD in the denominator and RC4 in the numerator, okay, and RD is of the order of 1 kilo ohm, similar to this. Of course, more current it flows, we know the current versus voltage curve, by which at higher current the RD value will come down. So, this will not remain exactly at this particular value, but gradually this denominator will become less, but for our calculation, approximate calculation, this is sufficient. So, 1 kilo ohm in parallel, so that is 0.5 kilo ohm, and we get the gain of minus 2.8 from this part, okay, for this part of the gain. Okay. Now, when this one is conducting, is an active region, this is also providing a voltage gain. Okay. So, this voltage gain is at the output with respect to voltage changes that is occurring at the base of T3. Okay. And this can be calculated as the beta forward, that is again this is, if this is your RD, beta forward is nothing but in that H parameter terms is HFE, okay, HFE, or we know the current gain, that is the beta in the forward direction, forward active mode of the transistor. Okay. So, at that time what is happening? So, this beta forward and the collector resistance at this for this particular transistor and the base emitter across this the resistance that is there, which is HIE or RD over here, the way we have represented it. Clear? So, this is the AB3. Now, this RC3, effective RC3, how do you calculate? You calculate as the resistance seen and this resistance, diode resistance, drop this resistance over this base emitter junction resistance, as well as this RC4 divided by the beta forward is the effective collector side resistance for this calculation, which happens to be minus, and if you just substitute the values, minus 3.4. Okay. And the gain over here in this cascaded stage is gain forward coming from here, change in delta V4, okay, and change coming from this, right. And this delta VB4 and delta VB3, the change over here and the change over here are same because of the emitter follower, that kind of, you see the whatever change will occur, the same change will occur over here. So, effective gain is summation of these two, and we get an approximate slope of minus 6.2, which of course increases towards when more and more current starts flowing through it. Okay. So, this is how the third zone occurs, and the T3 saturates at this particular transistor, saturates at when this reaches a voltage 0.75 volt. Okay. So, this is 0.75 volt, this saturates before T4 0.75, 0.7, okay, and at the input side minus 0.1, that is the voltage that you will see, which is 1.35 volt over here. Okay. Is it clear? This is the 1.35 volt that you see from the input side. From VB4 side, it is 1.45. Okay. So, this is the point C, that is how it is defined. So, Vi still getting increased, what will happen? Now, T4 will go also into saturation, and that is the voltage, that time voltage will be 2 into 7.75 minus 0.1, that will be the Vi at that time, and corresponding VO will be 0.1 volt. And if you keep increasing the voltage, then what will happen? This transistor will be working, it will be sending current in this direction, it will work in the reverse direction. This emitter will work as a collector, and this collector will work as a emitter, and the current will be going in the other direction, right. And for that the inverse beta will be very small value. Okay. So, if you now look at the whole of it, the normal stable operations are, this is the region 1 and region 4. Okay. And in this region 1 and region 4, what we see, how this T4 conducts. So, in region 1 we have already seen that T4 is off. Okay. When T4 is off, this is high in terms of making this transistor on, and this one is low. Okay. That is in region 1, and the other stable condition is region 4, and at that time what is happening in that particular condition in region 4. So, this is in saturation, right. So, this time this is low in terms of making this on, these two transistor on, and this is high in terms of making this transistor on. Okay. So, this transistor is on. So, 0.75 volt, 0.2 volt here, 0.95, which is not sufficient to drive both this transistor and the diode together on. So, this transistor will be off. Okay. So, in that sense, in that perspective, they are, when one is low, another is high, and when one is high, the other one is low. So, they remain out of phase in that sense, that is why it is called phase splitter. And we have already noted in this particular zone, briefly this T2 and T3, both of them are active, okay, for which there is a path from 5 volt to ground, when both the transistors are and diode is on, and that the resistance over here we need to make it some finite value, we cannot make it 0, because otherwise large amount of current will flow and power dissipation will be there. Okay. Now, we look at the one practical. So, I said that was an estimated value. So, if you look at any standard manufacturer's data sheet, we shall see that how the TTL gate inverter 7404, okay, what are the different parameters, how that is been specified. Okay. So, we are already familiar with the terms like VIH, VIL and so on. VIH is the minimum voltage at the input side which is considered as high. Okay. Any voltage above that is considered as high, there is no issue with that. Okay. So, if we look back this previous one, so VIH according to the manufacturer for different considering the typical loading and all. So, the value is considered for the minimum case is 2 volt. Okay. So, at the input side when it is 2 volt and above, right, it is considered safely as input is considered as high, that means it will give a generator output which is low. Okay. Similarly, VIL, input maximum value of the input voltage which is treated as low, any voltage less than that will be treated as low. So, if you look back at this value, so 0.8 is somewhere here, okay. 0.8 is somewhere here, right. So, sorry, 0.8 is somewhere here. So, at that time the output is somewhere here. Okay. So, any voltage less than that is treated as logic low. Okay. Okay. Similarly, VOH, VOL, all these terms we have defined before, and these are the corresponding values that the manufacturer will give you. Okay. And from that what we can do, we can arrive at the noise margin low and noise margin high as per the definition that we have discussed in the very first class, okay, and in subsequent classes, and from that we can see for the TTL the values are 0.4 volt and 0.4 volt. Okay. This is according the manufacturer's data sheet. In addition, you can see the corresponding current values, okay, for these different cases, and one such calculation where we can one such thing that we can see for fan out calculation here is the case where you can see this is the totem pole output and similar gates have been connected at the output. Okay. So, the IOL, right, now when you talk about this this sign of the current. So, any current that is going into is considered positive and going out of is considered as negative. So, IOH is the current that you can see, right, which is considered positive. So, let us start with IOL only, because in this example IOL is there. So, IOL, when the output is low, the current that is being sunk in. So, current being sunk in IOL is 16 milliampere. So, that is the maximum current it can sink. Okay. So, that is, and this it is getting into, that is why it is positive, right. So, this is the 16 milliampere, and for the load side similar circuit that is there. So, IL which is coming out of it, what is the corresponding value according to the specification given by the, that is minus 1.6. It is because it is coming out of it, okay, and it is getting into, right. So, how many such then load gates can be serviced by this? So, this is IOL by IL, right. and the other case happens when this is off and this is on and the current is driven in this direction and this is in inverse mode. We know that the current, this is going in this direction, inverse mode. So, that time the current that is at the load side, that is your IIH, is of the order of 40 microampere. The current that is going when this transistor is operating in inverse mode, that is the beta IB of T4. Okay? And corresponding IOH, which is coming from here, that is IOH in that case, right, for corresponding IIH. Okay. So, what is the value? That is given as G minus 0.4 milliampere. Okay. So, again it is going out. So, that is why the sense is negative, sign is negative. So, how many such gates can be serviced? So, again you take the ratio, right, and the fan out will be lower of these two numbers, and in happens to be case that the way the circuit has been designed by the manufacturer, it is same in both the cases. Okay. And for this particular gate, the power dissipation is of the order of 10 milliwatt. The other two important parameter is the propagation delay. So, propagation delay high, low to high. Okay. The value you see 12 nanosecond and 22 nanosecond, it depends on the loading. Okay. More such loads, more such capacitors will be coming in parallel and more time will be required. Okay. And the other reason for which low to high is more compared to high to low, that we have discussed before, that the time it takes to bring it out of the saturation, okay, which is more in case of the transistor going driven into saturation, from saturation to cut off the charge distribution that is required. And P high to low is the case when you have got the case which is relatively low, and this is measured under some specific condition. Okay. Now, TTL open collector, how does it work? So, in the TTL open collector, the last stage in the totem pole, you do not have any resistance. Okay. So, this remains open. So, to make it work, we need to connect an external resistance to it. Okay. So, this is the external resistance through it. So, this is called pull up resistance also. Okay. Now, by varying this resistance, we can vary the amount of current, and if you are connecting say a light emitting diode over here which requires more current, and corresponding resistance values can be decided here to make it glow. So, that is one good thing about it. The other aspect of this open collector configuration is that if you connect two such gates, so this is say one gate, right, and there is another gate, and you are connecting, just ANDing these two output. So, together if you just analyze, you see that they will give you a wired AND connection. So, these two, another such gates is there, right, and you just connect it over here, it will give you a wired AND connection, which is also useful in some cases. So, this is one important thing about open collector configuration. So, there is another use of TTL, the thing that we discussed earlier in terms of tri-state. Okay. So, in tri-state, that means the output is neither able to drive current nor able to sink current. Okay. So, that is called the tri-stated kind of thing. Okay. So, neither high nor low, it is kind of electrically isolated. So, when this enable is low, logic low, 0 volt or so, what will happen? In this particular case, you see for any of these cases, this particular transistor will be, this current will be drawn in this direction. So, this transistor will be off. Okay. So, this transistor is off. So, at that time this can become high in earlier in a normal operation, right, but because of this diode, which clamps the voltage to 0.7 volt and 0 volt over here, which is not sufficient to make both of them on, for which this transistor is also off. So, both of them are off. So, when enable is 0, both of them are off in the totem pole output. Only when it is high, okay, then it serves the normal operation of a inverter. Okay. So, this is the tri-stated TTL, which is also useful in many circuit. So, we shall look at TTL NAND gates we have already seen, right. So, TTL NOR gate, if you look at the manufacturer specification. So, again I have taken from a Texas Instruments SN 7402 technical document. So, what you will see here, these two input stages are in parallel and these two phase splitters are in parallel, okay, and the totem pole part is common. And NAND gate, of course, this is the multi-emitter NAND gate. So, this is how the TTL NAND gates and NOR gates are prepared, okay, and the operation is known. And you will see in these cases there is a input diode over here which actually prevents ringing due to transmission line termination issues. What can happen when you are taking it from high to say low, right. So, it may not, there may be a ringing. So, these diodes actually when it goes sufficiently low, this particular thing, so it conducts and it takes away the energy. So, this is another important thing that we need to know in the as a practical case. And the last topic that I would like to just mention here in today's class is the use of Schottky diode in the TTL configuration. Okay. Schottky diode is a metal semiconductor junction and it can provide a cut in voltage in the range of 0.2 to 0.5 volt. So, this is clamped, this is used between base and collector of a transistor, and this transistor, because of this, okay, this voltage is clamped to say 0.35 volt if you manufacture in that manner, and this is your 0.75 volt. So, this is 0.4 volt or so, which prevents it getting into saturation, so as to say. Okay. So, just stops short of saturation, which is useful in the sense that it helps in bringing it out of the saturation, the time the switching speed increases. So, that is one important thing where all the transistors that are supposed to saturate, right, that are changed using a Schottky diode. Okay. So, this is 74S00 again taken from the data sheet. So, you see these transistors are changed by Schottky diode. Okay. In addition, over here what you see is that earlier there was only a resistance, okay, from this T4. Now, there is a active pull down. So, this helps in taking away the charge from this base emitter junction when it is coming out of saturation. I mean, whatever level it goes into the saturation. And the other thing over here what you see is a Darlington pair configuration over here, and you do not need a diode over, because there are two such things. So, it also helps in providing larger amount of current. So, this configuration over here together with the Schottky clamped transistors used as a whole increases the switching speed, and the switching speed that we get here is of the order of 3 to 4.5 nanosecond depending on the test condition, and that is very useful for enhancing the transition speed. So, finally, to conclude, so what we have seen today, TTL transfer characteristics, its 4 distinct zones, how it works and its different operating parameters. We have seen that TTL NAND gate is obtained from multi-emitter input, while NOR gate is obtained by paralleling the input transistor and the phase splitter. Open collector configuration we have seen that it requires an external pull up resistance, and it can be also used for wired end configuration. TTL tri-state we have seen that when it is disabled, none of the output transistors in the totem pole configuration is on, and Schottky TTL does not allow the transistor go into the saturation, it just stops short of saturation, which enhances the switching speed. Thank you.